Good morning to everybody, and thank you very much to the organizers for inviting me. In this talk, I will talk about inverse quantum annealing, which is an adiabatic quantum computation technique that is used here for reconstructing the parent Hamiltonian of a quantum state. So in the first part of the talk, I will present our problem, which is an inverse problem and is an inverse many-body problem. And I will show in which the problem consists and why it is useful and which are the proposed solutions in literature. The idea is that here we start not from a many-body Hamiltonian, but from a many-body quantum state, and we want to find an Hamiltonian having this state as a ground state. But we also ask that this Hamiltonian is a physical Hamiltonian, and in particular we ask that this is a local Hamiltonian. So I will call parent Hamiltonian a local Hamiltonian having the target state as a ground state. And as you can see in the simple example, finding a parent Hamiltonian, a local parent Hamiltonian for a separable state is simple. You can just find a parent Hamiltonian for each local state and just overlap all the parent Hamiltonians. But if you want to solve this problem with a non-separable state, with an entangled state, then you need to invent something more sophisticated. And so this is a many-body quantum inverse problem. It is an inverse problem because this time we don't start from the Hamiltonian, but we start from the state and we look for the Hamiltonian. And it is a quantum problem, and it's important that it is quantum because, as you can see, the source of complexity of this problem is the entanglement in the target state. And it is also important that this is a many-body problem. Indeed, the computational complexity of this problem will increase a lot with system size if you look at generic quantum states. And why this is an important problem? There are, first of all, some technological applications, for example, quantum state preparation and also Hamiltonian learning. For example, if you have a quantum system in which you want to prepare a quantum state and you can implement a local Hamiltonian, then you can start from your target state, find a parent Hamiltonian for the state, implement the Hamiltonian in the system, and then prepare the state by cooling down the system or by adiabatic preparation. But this can also be applied to Hamiltonian learning. For example, if you have a system in which your Hamiltonian is local and you are at low temperature, the idea is to perform some measurement on the state and then try to infer the parent Hamiltonian which is governing the evolution of the system. But there are also some related theoretical questions to this problem. For example, one question is which are the observables, the information in general that we need about the state to find the Hamiltonian of the system? Do we need a full information of tomography of the state, or for example, only local expectation values are enough? And there is another interesting theoretical question that is how many solutions has the inverse problem? And it can be viewed as with a physical interpretation as can we deduce infer the high energy behavior of a quantum system from its low energy behavior? And finally, there are some future perspectives that are related to this problem, for example, the application to the quantum marginal problem. I will return on this point at the end of the talk. Now, this is an interesting problem, and for this reason there have been proposed some solutions in literature for different classes of states. Each of these solutions works well, efficiently for a certain class of states. For example, a possible approach works with tensor network states for which we can efficiently reconstruct frustration-free parent Hamiltonians. But there are also more generic approach. For example, we can reconstruct efficiently the symmetries of a state, and here in this context with symmetries I mean all the Hamiltonian having the state as an ideal state, and then we can diagonalize this Hamiltonian to look which Hamiltonian have the target state as the ground state. And as you can imagine, for many classes of Hamiltonian, this is computationally very hard. And there are some other approaches. For example, there is a method that is based on the Bisogniano-Wickman theorem from high-energy physics that is used as an ansatz in a many-body system, but this approach does not work for a lot of systems. When this approach works, you can use this approach to reconstruct locally the current Hamiltonian by looking only locally at the quantum state, and this is efficient. And finally, there is a more generic approach, which is based on the optimization of a thermodynamic cost function. In this case, what you do is to take a candidate current Hamiltonian and you calculate the local expectation values of the low temperature Gibbs state associated to this Hamiltonian, and you try to minimize the distance between these local expectation values and the local expectation values of the target states. Also, this method works efficiently only for classes of candidate Hamiltonian which have a spectrum that allows for calculating the Gibbs state. And what we propose here is another method that works for a quite interesting class of states, which are states with short-range correlations. Our method will be an adiabatic quantum computation method based on an adiabatic dynamics in the space of Hamiltonians, and here I will introduce the method and how it works. The method is inspired to...
Yeah, I have a question. Could I have a microphone, please? Sorry. No worries. Thank you. So I'm just wondering, before we continue to your work and what you did. So, given any quantum state, the number of Hamiltonians that could have this state as its ground state could be infinite. So, how do you determine, or what other constraints are you putting on your solution to make sure you converge to a single or finitely solutions?
Thank you. In this work, we only ask to find one of the infinite parent Hamiltonians that a state can have. And since we will use a dynamical method, this will automatically find just one solution for the problem.
Okay, thank you.
And our method is inspired to quantum annealing, and in particular, as we know, the goal of quantum annealing is to solve a forward many-body problem in which you have a many-body Hamiltonian and you want to find a ground state for this Hamiltonian. So what you do is to take a different Hamiltonian for which you can find a ground state, you prepare the ground state of this different Hamiltonian, and then slowly interpolate from this initial Hamiltonian towards the Hamiltonian for which you want to know the ground state. And the Schrödinger dynamics with the adiabatic theorem ensures that if you are slow enough, you will end up with your target ground state. Here we want to do the same thing, but with the role of the state and the role of the Hamiltonian swapped. So what does it mean? It means that we take a final state for which we want to reconstruct a parent Hamiltonian, and we take an initial state for which it is easy to reconstruct a parent Hamiltonian. Then we choose a path of states connecting the initial state to the final state, and we use a dynamics that is determined by this path of state to evolve the initial Hamiltonian, which is the parent Hamiltonian for the initial state, towards the final Hamiltonian, which is the parent Hamiltonian for the final state. And as you can easily see, here there is something that is strange, because in the standard quantum annealing law, you are doing something that is natural. You are evolving a system state with an Hamiltonian, and there is a natural dynamics, which is the Schrödinger dynamics, that tell us how a Hamiltonian determines the evolution of a state. Here instead, we need to invent an artificial dynamics that works for our purpose, and this is what we did in this work. So I will now introduce this artificial dynamics, then I will show why and that this dynamics works for our purpose. So first of all, we choose a path of states. So we need a path of states that starts from a state for which we know the parent Hamiltonian and ends up in a state for which we want to know the parent Hamiltonian. We also choose a monotone annealing schedule from the initial state such that at the annealing time t, the corresponding state is the final state. Now we need to introduce a dynamic and this is our artificial dynamics. This is a unitary dynamics for the Hamiltonian of the system, where the generator of the dynamics is the projector on the path of quantum states. You can look at this dynamics as a von Neumann dynamics for the density matrix of the system, but with all of the Hamiltonian and the role of the state is swapped. And we impose as an initial condition for this dynamics that the initial Hamiltonian of the system is the parent Hamiltonian for the initial state. Now the first step is to show what happens to this dynamics in the adiabatic limit. And so we start with dynamics, and we know that if we do spectral decomposition, the ground state of the initial Hamiltonian of the system is our terminal state. Now, this is a unitary dynamics, so there is a unitary operator that is evolving our Hamiltonian, and this operator is given by the time-ordered exponentiation of the projector to the path of states. And since this is a unitary dynamics, during the evolution, the spectrum will be preserved, and each eta state evolves separately. So if we want to understand which is in the adiabatic limit the ground state of the generated Hamiltonian, we need to look at the effect of this unitary operator on the initial ground state. And here the adiabatic limit comes into account, and we can use the adiabatic theorem to show that in the adiabatic limit the initial state will be transformed into the states of the path. And this is because the pseudo-Hamiltonian pi that is generating the evolution has the path of states as a unique and as a non-degenerate quantum eigenstate. So now we will consider this adiabatic limit, and I will call this Hamiltonian the adiabatic Hamiltonian of the system. What I've shown is that this Hamiltonian has the target state as the ground state, but as I said initially, this is not enough. We also want an Hamiltonian that is a local Hamiltonian. So now we need to answer to a question, and this question is the initial locality of the Hamiltonian preserved during the adiabatic evolution? Before answering to this question, I would like to be more clear about what I mean with locality. When I say a local Hamiltonian, I mean that there is a set of Hermitian operators that acts on a lattice of particles, and I ask that the maximum range on this lattice does not depend on the size of the lattice. And if you have this kind of operator, this kind of Hamiltonian, you can write this Hamiltonian as the span of these operators, and the Hamiltonian is uniquely defined by the coupling associated to these Hermitian operators. And here it is important to remark that the number of these couplings, as well as the number of local operators, is polynomial in the system size. And now let us go to our main problem: is the locality preserved? Here we don't have a general proof. We have a physical expectation that does not work for all the states, but works for a lot of interesting situations. Here I will give a theoretical justification, a theoretical argument for this expectation, and then I will show that it works at least in the examples studied in this work. And the physical expectation is that when the path of states that we choose has a finite correlation length, then the adiabatic Hamiltonian generated by the method will be a local Hamiltonian. And the physical reason behind this expectation is that if your ground state has a finite correlation length, this state encodes some notion of locality and some notion of distance for the lattice. And is highly unlikely for the parent Hamiltonian of this state do not encode any notion of distance for the lattice. So now we have two ingredients. We have a parent Hamiltonian having the state as the ground state, and we also have that this is a local Hamiltonian, but there is a problem. And the problem is that our dynamics, the dynamics that we have defined, we cannot integrate these dynamics. This is a quantum dynamics. We need an exponential amount of degrees of freedom to integrate these dynamics, and we actually don't have a quantum computer that is useful to integrate this kind of dynamics. So the idea here is to perform an equivalent dynamics and approximation that can be integrated with a classical computer. And the idea here is to exploit the locality of our solution. So if it's true, our assumption about the preserved locality, it is also true that the adiabatic evolution moves into a space that is expanded by a polynomial number of Hermitian operators. So what we will do is to project the time evolution defined in this equation to this space with a time-dependent variational principle. We can do this because we have an Hilbert-Schmidt scalar product in the space of Hermitian operators. And what we expect is that if it's true that in the adiabatic limit the evolution preserves locality, then the approximation defined with this time-dependent variational principle will be negligible. In this way, we obtain a new equation that is an evolution for the couplings of the Hamiltonian. So now let us focus on this equation. This is our evolution for the couplings. This is a differential equation where the generator of the dynamics is a matrix. I will call this matrix commutator matrix because it is a matrix of expectation values of commutators of local operators. And we expect that if we choose a path of states with finite correlation length, if we integrate this equation in the adiabatic limit, we will approximate a local parent Hamiltonian for the states of the path psi lambda. For this reason, from now on, I will call this dynamics inverse quantum annealing. And before going on with examples, there are some silent features that I would like to stress. The first one is that, as I argued, we expect a negligible approximation due to the time-dependent variational principle when we cross a path of states with finite correlation length. The second thing is that we only need the local expectation value to reconstruct a parent Hamiltonian with inverse quantum annealing. Indeed, here you can see a matrix of expectation values of commutators of local operators, but commutators of local operators are local operators. And finally, this equation can be now represented and solved using a polynomial amount of memory, because you need only to represent a number of variables that scales with the number of linear local operators. So now let us show that this works, at least in the examples that we have tested. The first example that I would like to show is a path of states which are Gaussian states. The reason for which we choose these examples is that at a certain point in this path of states, there are states with long-range correlation. So what we expect is that previous from the state, if we did not cross the states with long-range correlation, the inverse adiabatic method works, and we can find a group parent Hamiltonian, and we expect to fail when we encounter long-range correlations. So we will choose a path of states which is defined as a path of ground states for a 1D type model. This is a one-dimensional fermion chain, and without keeping any information about this initial Hamiltonian, we will use inverse quantum annealing with the path of states psi lambda to reconstruct a local parent Hamiltonian for each state of this path. So why choosing this kind of model? The first reason is that a local parent Hamiltonian exists, and it is the key type Hamiltonian, and for this reason, if we are failing in finding a parent Hamiltonian, this is not because there is no parent Hamiltonian, this is because we are failing. And the second important thing is that the solution can be also verified efficiently for this problem. Indeed, when we find a parent Hamiltonian in the space of a quadratic fermionic Hamiltonian, we can also verify that this is a parent Hamiltonian by efficiently calculating the ground state with Jordan linear transformations. And finally, as I anticipated, this path of states has long-range correlations at the critical value of lambda equal to 1/2. So we can test what happened before we have long-range correlations and after. So which are the settings in which we test our method? First of all, we will choose a linear annealing schedule with different final annealing time to check how the convergence to the adiabatic limit happens. Then we will choose different notion of localities, and in particular different interaction ranges, from short-range interactions to all-to-all interactions. For each interaction range, we choose a basis of operators with that maximum interaction range. In this way, we can test what happens if we do time-dependent variational principle, and also what happens if we don't do any kind of projection. And finally, we will test how the main figure of merits of our method scales with the system size. So the first thing that we want to look is the convergence to the adiabatic limit. To measure this convergence, we look at the distance at different annealing times between the corresponding solution of the adiabatic equation. When this distance goes to 0, we are converging to the adiabatic limit. And what we can see in the left-hand side figure is that this distance for a system of 50 spins and different annealing time has the typical oscillating behavior of non-adiabatic processes and is converging to 0 with a peak corresponding to the phase transition. And the second thing that we can see is in the right-hand figure, where we plot how the maximum value of this distance depends on the system size and depends on the annealing time, and we can see that the non-adiabatic effect scales as 1 over the total annealing time. Now, what about, before going to the results of the real application of the method with time-dependent variational principle, I would like to show if it's true that the locality is preserved at the 4 states with local correlation. So in this slide, I don't use any time-dependent variational principle, and I look at the adiabatic Hamiltonian generated without any projection. And I want to check if this Hamiltonian really is a local Hamiltonian, and to do this, we look at the magnitude, the total magnitude of the couplings associated to the operator of each range. And we can see here that for a system of 40 spin and for a system of 60 spins and for different value of the control parameter, the generated Hamiltonian has couplings that decay exponentially with the range, with exception for the critical state. So for the non-critical states, for states with short-range correlation, we have exponentially decaying interactions. Moreover, the shape of these lines does not depend on the system size, and this means that it exists an effective interaction range that does not depend on the system size. Let us be more quantitative. To be more quantitative, we can look at this decay rate that is defined here, and we can plot this decay rate as a function of the control parameter and as a function of the system size. And what we can see is that for non-critical states, this decay rate does not depend on the system size. This decay rate is indeed very similar to what we expect for the correlation length of the states of the path. And we can also investigate which are the dynamical reasons of this behavior. To investigate the dynamical reasons, we can look at the generator of the dynamics, that is here the commutator matrix. If we look at the non-diagonal elements of this commutator matrix, we can see that these non-diagonal elements decay exponentially with a rate that, again, is independent on the system size for non-critical states. So we can conclude that for non-critical states, the dynamics weakly couples the states which correspond to local operators to the states which correspond, to weakly couples the space of local operators to the space of non-local operators. Indeed, they are the non-diagonal elements of the commutator matrix that couples these two spaces. Now let us go to the main figure of merit, that is the fidelity after the time-dependent variational principle. And here I plot this fidelity for a system of 50 spins and for different values of lambda. The different proofs correspond to different notion of locality. Here the red one is a locality where you have only nearest neighboring interactions, where the yellow one it means that you have no locality and no time-dependent variational principle. And how can we look at the figure of merit? We can look at the fidelity between the ground state of the generated adiabatic Hamiltonian and the target state. If this fidelity is high also for short-range interactions, you have a good local parent Hamiltonian. If you need a long-range interaction to reach a high fidelity, you don't have a good parent Hamiltonian. And here you can see clearly that there are two different behaviors. A behavior before the phase transition, where when everything works good, then you have a good parent Hamiltonian, and after the phase transition, when you cannot have a good parent Hamiltonian. And this kind of behavior is also reminiscent of what happens in the standard quantum annealing. Indeed, here, long-range correlations are an obstacle, as well as in the standard quantum annealing, closing energy gaps are an obstacle. To be more quantitative, we can define an acceptable interaction range. What is the acceptable interaction range? Is the minimum range that we need to reach a target fidelity. So we choose a tolerance epsilon and we define the minimum range needed to have a fidelity greater than 1 minus epsilon. Here I plot the behavior of this quantity for different system sizes and different values of lambda. And here again you can see two different regimes. If you look at values of lambda before the phase transition, you can see that you have weak dependence on the system size. This means that you find a local parent Hamiltonian and also that your time-dependent variational principle need to project only on local operators, so you also can reach this Hamiltonian in a polynomial computational time. Instead, if you look after the phase transition, you will have an interaction range that scales with the system size, so your Hamiltonian is no more local and you cannot implement this method efficiently. So now I would like to show another example, and this example needs to solve some questions that have been raised by the first example. The first question is, the first objection is, okay, but this is an integrable model, we can just find an Hamiltonian analytically for this model. And the second objection is that we are crossing long-range interactions, so our method did not work for the final state, and now I want to show something that works also for the final state. For this reason, I will choose a path of states that again process a phase transition, but a first-order phase transition. So let me introduce the model. Here we look at the path of ground states of a Nielsen chain with the transverse and the longitudinal field. And again, we don't keep any information about the Hamiltonian. We start from just the initial Hamiltonian and we perform inverse quantum annealing to find parent Hamiltonians for the state psi lambda. And in this case, we will only use interaction with maximum range 2, so very local interactions to construct our parent Hamiltonian. And why this model? There are many reasons. The first reason is that this model is an integrable model. So, is not an integrable model. So there is no way to find generically a solution by analytical methods. And the second interesting thing is that this model now processes a phase transition at the critical value of lambda equal to 1/2, but this time the phase transition is of the first order and you don't have long-range correlation. So if our hypothesis about the preservation of locality is true, we expect to find a solution also for the final path, the final state of the path. And this is what we find at the end. Here in this figure, I show how the infidelity behaves as a function of the total annealing time and for different system sizes. And here you can see many interesting things, but the most interesting one is that if you look to a sufficiently large annealing time, so if you go to the adiabatic limit, you will recover a state with infidelity 0 and fidelity 1, also for a large system. And this means that all the process of inverse quantum annealing works, and it works because we don't have states with long-range correlations. Another thing that you can see here is that here is clear the dependency of the total annealing time on the system size. Indeed, if you look at the larger systems, you need more annealing time. And finally, again, as before, for large annealing time, the final infidelity decays polynomially as a function of the annealing time. So now I can devote some to the conclusions, and in particular to stress the strength and the limits of this method and some interesting future perspective. So what we have done is, first of all, to extend quantum annealing intended as adiabatic quantum computation and adiabatic quantum dynamics to the solution, from the solution of the direct problem of finding the ground state to the solution of an inverse problem. Second, our method efficiently generates a local parent Hamiltonian. Obviously, there is no free lunch, so this method works for a class of problems, and the class of problems is states with the finite correlation length. And finally, our method only needs the knowledge of local expectation values, so we only need knowledge of local expectation values to find the parent Hamiltonian. But there is a price that we have to pay, and the price is that we need to find a path of finitely correlated states that connect the initial state for which we know the solution to the final state for which we want to know the solution. And this also opens the first important challenge for our method, that is selecting the path of states. We need to invent a way to select this path of states, and this is also reminiscent of what happens in standard quantum annealing, where you want to select a path of Hamiltonian to generate your solution, and is good if you can select a path of Hamiltonians where you don't find any state with where you don't find any closing energy. The second thing that, the second future perspective that I would like to show is the relation between inverse quantum annealing and the quantum marginal problem. In the quantum marginal problem, you start from knowledge of local expectation value in this case, and you want to infer the non-local expectation values. This thing can be done easily from some classes of states. For example, for Gaussian states, you have the weak theorem that tells you how you can reconstruct the expectation values of strings of operators from the knowledge of 2 points correlations. But for generic states, there is no way, no general way to solve this problem. So a possible idea, if you are working with a finitely correlated state, is to combine inverse quantum annealing and quantum annealing. Indeed, with inverse quantum annealing, you can start from knowledge of local expectation values and use this knowledge to find the parent Hamiltonian of the system. Then, with quantum annealing, you can use the knowledge of the parent Hamiltonian to find the ground states of this Hamiltonian. And at this point, you have implemented the system state with the adiabatic dynamic, and you can just measure annealing and quantum annealing to solve the quantum marginal problem. And there is another future perspective that is a far future perspective and is related to the quantum implementation of our dynamics. Indeed, initially I presented an adiabatic dynamics, and I argued that in the adiabatic limit, these dynamics give us a local parent Hamiltonian. And it gives us a local parent Hamiltonian also for states with short-range correlations, even if the path of states passed through a state with long-range correlation. So if we can directly implement these dynamics without time-dependent variational principle, then we can find a solution also for path of states that cross a second order phase transition. And in principle, there is an algorithm that could allow to implement this kind of dynamics, and it is the density matrix exponentiation algorithm. Indeed, with this density matrix exponentiation algorithm, you can evolve a many-body state with the unitary matrix that is obtained by the exponentiation of another many-body state. Thank you.
Okay, thank you for the talk, Davide. We are now open for questions.
I don't understand one thing. Why did you say that you need long-range Hamiltonians to generate states with long-range correlations? Because there are Hamiltonians which are short-range critical points which are long-range correlated.
Yes, indeed. As I said, there are some exceptions. Indeed, if you look at critical points, you are looking at a slightly fine-tuned situation. So what they expect is that it can happen that you cannot find the Hamiltonian with the short interaction range. But there are many interesting physical situations in which you will end up with the right Hamiltonian.
So you're saying that generic long-range correlated states are not the ground state of a particular short-range Hamiltonian?
Yes, by generic you mean that this cannot be extended to all the states. Yes, this is what I mean.
Well, 2016, I also have a question. So this is regarding the paths you were discussing, and actually for So how this annealing, you have this dynamics, that was like annealing dynamics, and what is the gap here? Because if I look at your Hamiltonian, it's always a projector, right? What is going to matter was projectors. I wouldn't see any gap that I have to adjust, right?
Yes, here the problem is not directly in the gap. If you want to look at the gap, you need to look at the commutator matrix. The commutator matrix has been obtained by the projection with the time-dependent variation of principle. So the real reason for which you are failing is that your dynamics is no more in the space of local Hamiltonians. And for these reasons, your projection is changing your initial gap that as you just said, was a gap, always open gap, and is changing this gap. But the way in which this gap changes depends on your choice of the path of states, and in particular on the correlation length of your states.
I see, so it's because of the approximation.
Yes, it's because of the time-dependent approximation. And then there is another possible source, but this time it's not the gap, is how fast the matrix element of the matrix K are changing. It is like the numerator in the lambda-Wiener probability of transition.
Any other questions?
It seems to me that this equation here on the left is nothing but the one that you would have for counter-adiabatic driving actually. If you replace I with your counter-adiabatic Hamiltonian, that should be exactly the same thing. Did you think about this connection?
Not directly, but now what I can say is that there are relationships between the counter-adiabatic driving and the evolution of Hamiltonian in this method, and indeed the kind of matrix that you find in this method, for example, when you find the commutator matrix, is similar to contains the same commutators that you will use if you try to generate a local counter-adiabatic driving by projecting on the space of local operators the Berry connection.
And so, if this is the same thing of counter-adiabatic driving, why does it fail if you drive slowly? If you don't drive slowly, you should be constructing the exact.
Because the counter-adiabatic driving is a driving for the system state, while here you have a driving for the system Hamiltonian. So I don't have a direct answer, but I think that this connection is not so direct that we can just take conclusions from one approach and apply also to the other approach.
Okay, so if there are no further questions, let's thank Davide again.